In this tutorial, we're going to explore some audio visualization techniques to create this dancing polygon. And this time we'll be using Skia, the 2D rendering engine that comes with vvvv by default. Here's what's going to happen. The polygon will jump to random points on the canvas whenever a bass drum kicks in, and every time this melodic synth plays, it will invert its colors. Along the way, I'll share some tricks for animating and filtering values, plus how to use random generators to keep the visuals dynamic, unpredictable, and constantly changing. Our first step would be to reference VL.Skia, which we'll use to draw the polygon, so select the renderer from the node browser. Set its background color to any color you like. In my case, I chose this intense neon yellow. Also place the polygon node and connect its output to the renderer. Now, if you're wondering why nothing is showing up yet, it is because we have not specified any points which the node needs on this input. As an example, we can use a random spread 2D node to generate a random set of positions. The polygon then draws the shape from one line to the next, and we can also set the closed input to true, so the last and the first point also get connected. Additionally, send in a stroke node with its color set to black in order to draw the polygon with a solid border. In our case, we actually don't want to spread the points randomly, but instead they should have a linear distribution along the vertical axis and a random horizontal position out of 3 possible choices. Either to the left, in the middle, or to the right. Let's generate the Y positions by creating a linear spread with a count of 5, which returns floats with equal distances, and send them into a for each. Also, we're going to use another linear spread to create the possible horizontal positions. In order to use one of these in each iteration, we will send this spread into a get slice and, just for now, use the current index of the loop. If we then join these two values coming from the get slice and the splicer input of the region, we can leave the loop, collect the vectors in a spread, and connect it to the input of the polygon. And in order to make the point stretch across the whole renderer, let's expose and increase the width input of the linear spreads. In comparison to the random distribution of positions, we can now see that the X positions keep on repeating in the zigzag pattern, because the get slice will start again from the beginning of the spread if its index is higher than the amount of slices. We can visualize this even clearer when also drawing a circle on the positions inside of the loop, so collect them with the group spectral, and combine its output with the layer from the polygon. Let's also send in a fill node for which we use the same color as for the stroke, and also decrease the radius of the circles to a smaller value. We can now clearly see that for each of the vertical positions, the next available horizontal position is taken from the other linear spread, jumping back to the first entry every 3 iterations. If you want, you can also increase the count of the vertical positions and show more of these points, but I will just leave it at 5 for now. However, we actually don't want to get the X positions sequentially, but randomly for each circle. We can do this by choosing the random node from the node browser, which is adaptive and can generate random values for different types, like floats, integers, vectors, and colors. In our case, we needed to generate random integers, so once we connect the node to the index pin of the get slice and create a range of integers between 0 and 3, the points randomly jump between these 3 positions. For now, these values are the same for each of the circles, because we have to set the seed of each random node to a different value. And in order to do this, we can simply connect the index of the iteration to the seed. Also, by default, the random node generates a value for each frame, which makes the circles jump around wildly inside of the renderer. But if you expose the enabled pin as a bang, you can control the execution of the node and trigger it from the outside. And by exposing the fourth input of the node and setting it to false, you can also prevent the random node to generate the same value when triggered repeatedly. As we also want to use the same trigger to generate a random size for the circles, we can copy both the random and the range nodes and connect them to the radius pin instead. Make sure to send in values in a meaningful range and also connect the other pins to the same sources as before, especially the seed and the index, because also this random will generate the same values inside the loop if the seed is the same for each iteration. Right now, every time we trigger the random nodes, the positions and sizes of the circles jump to the new values, but we can also create a smooth transition by using filter nodes. To animate, for instance, this float that is returned by the getSlice and being joined with the Y position, insert a filter node right into the link. It will automatically connect to the second input of the node, which is the value the filter should animate to. Every time you now trigger the random node, the circle will make a linear interpolation from the old value to the new during the specified time, which you can set on the next input of the filter. And we can also use a second filter to animate the radius of the circles generated from the other random node, so both properties of the visual are now generated and transitioned from the same trigger. Besides the time, there are also some other settings available for the filter, like the transition type and mode, which will affect the curve of the animation. The default is a linear interpolation, which will just animate the values with the same speed, but if you, for instance, set the mode to in-out and the transition to sine, all transitions will start and end smoothly. Feel free to play around with these properties and set them to whatever you like. I will leave them at the type elastic and set the transition time of the radius a bit longer to have the snappy feeling in the motion, so the sizes will still change after they move to the new positions. Next, we're also going to implement a probability mechanism, which prevents the random nodes to generate new values on every trigger. And in order to do so, we will need a third random node, and if we simply connect it to a float I/O box without specifying any range, we can see that by default it constantly generates random values between 0 and 1, which we can send into a smaller than node and set the threshold for the probability on the right input. If we, for example, set the threshold to 0.5, approximately 50% of the time this condition will be false. And if we send both this boolean and the bang into an AND node, the trigger will only be forwarded if our comparison is also true. Remember, we need to set different seeds to avoid having the same values for all iterations of the loop, so also connect this random node to the index. Afterwards, you can play with this new probability value. The higher this value, the more likely the circles are going to change the position whenever the random is triggered. Before we go into audio visualization techniques, let's refactor the patch and make some space by cutting everything except the renderer and its background color. Create a new node with the name Dancing Polygon. Right-click and open the process and paste everything inside. And once we create inputs for the trigger and the color, and an output for its layer, we can connect it again in our main patch, expose the input pins and trigger the bang one time, so we see the visual again. We have finally come to a point at which we will set a reference to VL.Audio, as we are going to control the trigger and the colors using audio analysis methods. If you go to the link in the video description, you will find the track that I will use to follow along, so make sure to download it and then use an audio player with the loop and play inputs set to true, and an audio node to play it from vvvv. In case you don't hear anything, check out your audio input and output settings in the configuration extension, which you can find via the quad menu. We will start by using a meter node, which will analyze a mono audio signal and return its amplitude. And as you can see on the output pin of the audio player node, we are dealing with a spread containing two audio signals, as we are listening to a stereo track. So you can either get the left or right output from the track with a get slice, or combine both tracks into a mono signal with a 2 mono node, and once you expose the output of the meter, you can see that it generates a float representing the volume of the track. As an example, send the dancing polygon through a uniform scale of type Skia transform, and send the float into the right input of the node, which will affect the size of the polygon. And as the meter in this case returns some value between 0 and approximately 0.1, we can insert a map clamp to scale the value to another range and clamp it between the output values, in this case between 0.8 and 1. And in order to get a smoother animation of the scaling, you can use a damper node, which works similar like the filter node you've already been introduced to, only that it has a predefined transition behavior. This time we're using it to simply smoothen the signal coming from the meter with a rather short transition time. Just remember one thing: when it comes to values generated from audio analysis, there's nothing like a predictable range that you can always work with in any setup. The values and ranges returned from audio analysis vary between audio sources and individual hardware setups, so there's also a chance that this example has to be set to slightly different mapping values to get to the same visual result. While the meter returns us the current amplitude for the whole track, I would like to show you two more techniques with which you can extract information from a frequency range, and also for single frequencies, starting with generating a trigger from the bass drum for the positions of the circles. A common practice to do that is using a meter on an audio signal that runs through an audio filter. So let's type filter into the node browser, but this time select the one from the audio category. Just to quickly demonstrate what the audio filter does, this is how the track sounds when sent through the filter node and set to a cutoff frequency of something like 300 Hz. You can hear that all high frequencies are cut off and only those in the bass range are left. Note that we needed this cons node only to generate again a stereo signal for the audio out, but anyways, this was just for previewing the filtered audio signal. Let's keep on working with that while listening to the original track. We can now use another meter node on the filtered signal, which returns a float representing the volume of the bass frequencies in the track. And anytime this is over a certain threshold, we generate a bang with a talk edge and can use this to trigger the positions of the polygon. It is good practice in audio analysis to also debounce the boolean and erase jitters in the detected volume by using a monoflop in between the comparison and the talk edge and set it to a very low time. This will make sure that for the time specified on the monoflop, we won't get another bang. If we then connect this boolean to the trigger of the dancing polygon, they nicely change their positions every time a bass hit is detected. And finally, we also want to patch a trigger to invert both colors in the rendering using a swap and a toggle node. Whenever the toggle node receives a trigger on its input, the boolean on the output will be used to switch the outputs of the swap, and as a trigger we want to react on this melodic synth that you can hear every few seconds in the loop. Before we can do that, we should try to gather some information about the frequencies that are present in this sample. So VL.Audio comes with a little visualization tool that you can find via the extensions in the quad menu, and in there you see a spectrum of all audible frequencies of the audio output with some settings available. If you switch here to the logarithmic view, you get a pretty good understanding of what is happening in the track and can also detect a peak in this area of the spectrum whenever the synth in question can be heard. Also, in the visualizer, you get the information about the frequency you're hovering, which currently is around 320 Hz, and this would be the frequency of which we want to get the amplitude. So let's send the mono signal into an FFT node, which on its output returns a list of all available frequencies as seen in the visualizer. And if we send that list into a node called pick FFT frequency band and specify the frequency we have detected in the previous step, we now get the volume for it. If you look closely, you can see that whenever the synth is being heard, the value goes up, so we can simply copy and reuse the same logic from before, only this time with a higher threshold value, and send the trigger generated by the talk edge into the toggle node that swaps the colors. That's it for this tutorial. Happy to have introduced you to some common audio analysis and visualization techniques inside of vvvv. We're very curious to see what you will do with these, so please leave links to videos of yours in the comments, and of course also feel free to do so if you run into problems or have further questions. Until then, have a good patch.